Welcome to Lecture 29. This is again Stokes' theorem, but now we're going to do an application in which we make use of a delta function in 3D. The material here is from reading assignment 5, section 4.3. It's a solenoidal geometry with a circumferential current flow. Section 4.6 and additional problems in section 6. The objectives of this lecture are basically to apply Stokes' theorem for a magnetostatics problem, assuming a Dirac delta function for the source term J, which is the current flux density. Concepts visualization skills are to determine the direction of the field and the functional dependency of the field's magnitude, and to develop the procedure for determining the field given a current flux density flowing in a axial direction in an infinitely long helix. As usual, the second slide is just a summary of the slides to follow, so we'll just skip it. Okay, so this is a magnetostatic, a source-free problem in which we're going to basically make use of the Dirac distribution. And so the field equations, typically as stated in a previous lecture, we can either talk in terms of magnetic field or in terms of magnetic flux density. In both cases, there's a curl of a field and a divergence of a field. In our case, we're going to work with the magnetic field H, and we're just going to give it the label F, and we're going to basically refer to the label J subscript E as just capital J. That's for the current flux density, just to reduce the amount of nomenclature being used. So if we're going to apply Stokes' theorem, which is the case when we're dealing with a source-free type of system, and also we're dealing with a high degree of symmetry, then it'll basically allow us to extract the value of f out of this integral. And Stokes' theorem is going to be applied, which means we take a closed contour integral of the dot product between the field of interest and the tangent vector. And that's equivalent to taking the curl of that vector field and then dot product with the differential area and integrating over the area which is bound by this closed contour here. Now, in our case, the curl of f is known. It's a given. It's J. That's part of the problem statement. And so then it just comes down to doing the calculation on the right-hand side. And again, we're going to try and make use of specific problems in that if we can choose the surface area vector to be in the same direction as J, that makes this calculation that much easier. And don't forget that the surface area is completely an arbitrary degree of freedom, because as long as the surface area that we've chosen is bounded by the same contour, we can basically solve the problem. And so in our case, we're going to choose NDS to be in the same direction of J to facilitate the ease of calculations on the right-hand side. So here's our problem statement. Consider an infinitely long helical filamentary winding with winding pitch A in units of meters. That's basically the distance between turns, so as you wind your way up. And the radius of the helix is capital R. The axis of symmetry of the helical filamentary winding is aligned with the z-axis. The current flux in the filamentary winding is I. That means if you integrate the current flux density over the filament, the value that you get is I, and that would have units of amperes. And so the calculation procedure as before to compute F is as follows. First, determine the nature of the symmetry and determine if you need to use superposition. Secondly, determine the mathematical form of F and establish the shape of the closed contour. So we use symmetry basically to make our choice. Then compute the left-hand side of Stokes' theorem, followed by the right-hand side, and then equate the left-hand side and the right-hand side to compute the vector field F. All right, so let's start with a very simple picture to show how we make our life that much easier. So this is an example of the actual solenoid that we're looking at, and the current is basically flowing around in this direction. Okay, so it's winding its way down. So it appears that the current is actually flowing in an axial direction, but is more or less a current that is a larger component in a circumferential direction, as will be shown on your right-hand side. So using Stokes' theorem, we can basically determine what the direction of the field will be. Not only that, we have two other bits of information of use to us, and that is that the divergence of field will be equal to 0, which means that the field lines have to form closed circles or closed contours. And also the divergence J must be 0, which means the current has to basically return to infinity from infinity. So for instance, any current here at infinity will basically return and eventually end up here. All right, so we use the right-hand rule. So the thumb will point in the direction of J, which will be this way. And just if you take your thumb and follow along the direction of the contour, the fingers will continuously on the inside be pointing in an upward direction. So we know that the field lines on the inside of the helix are pointing upwards, but we know that the divergence of field is 0. So these field lines have to return infinity, form a closed circle, and come back to it. Now, the other thing is a finer point. If you look at a sort of a finite size solenoid, you'll notice that if you're close to the end, these field lines will come around. And if you're very close, there'll be a slight distortion here where they want to come, but then move on to the next one. If you're very, very close, then you form these little closed lines very close to the actual filament. And so this is actually what you would expect to see. If you only focus in this region, you swear basically there's no change taking place. So if you look across here, the field lines are equidistant with respect to each other. That means the field is uniform. Not only that, if you move in this direction, you see no change taking place, which means the field is uniform along this direction. So if we only look at this little segment here, we would say field is uniform this way and field is uniform this way. Now, as you get close to this, to the periphery, then we'd expect that to not to be the case anymore. But because we're considering as an infinite cylinder, then we can immediately see that the F in this region is constant along the Z direction. Out here, it's going to be vanishingly small. So you can almost say the field is 0 out here. And then also you'll notice that there's a periodicity here. So for example, if we look at a halfway point between two windings here and a halfway point between two windings here, that distance, of course, would be the pitch. You'll notice that the pattern repeats itself. So imagine going in this direction and then coming back in this direction. What you see in this direction is negated by anything you see in this direction. And so if we choose a contour which goes this side and then back on this side, where we basically preserve this periodicity, then this will make the contour integration very simple. So these are basically sort of ground rules. This, by the way, comes from an image file you can look at here if you wish. Now, this in itself is too difficult a problem to solve. And so what we'll do is we'll approximate the solenoid as a series of stacked coils, single turn coils, and the current is more or less flowing exactly in the same direction, which would have been in a counterclockwise direction. And we preserve the pitch between the windings. So this distance is A. So that's a certain number of turns per meter, a certain distance A. So the units here would be A, that's the pitch. And we stack them on top of each other. Now this problem is much easier to work with, in the sense that the distance between each of these more or less remains the same on both sides. So this is the approximation to the solenoid. And so this is just a sort of a summary of just what I've stated. So this is our picture that we're going to work with, the one on the right. All right, so the next thing is to establish the symmetry, to shape the closed contour, and to apply the conventions. And so as we discussed in a previous lecture, the criteria for choosing the shape of the closed contour, one of three options. The vector field F is parallel to the tangent vector on a contour segment, and the magnitude of the field F is constant each point on the same contour segment. Hence, F dot T ds is either the magnitude of F ds or minus the magnitude of F ds, and the magnitude of F being constant come outside the integral. Or the vector field F equals 0 on a contour segment, and hence F dot T ds equals 0, or thirdly, the vector field F is perpendicular to the tangent vector T on a contour segment, hence F dot T ds equals 0. So in this particular case, we're dealing with the infinite helical winding. We know that there's a field that's basically in the z-hat direction inside the helix, but it's 0 outside. And so it seems to be that a rectangular contour is the appropriate choice. And there are 4 sides. And so in this particular example, all 3 cases stated above under criteria apply. All right, so the rectangular contour consists of extending a segment beyond the helical winding and make it parallel to the z-axis. And then you have one branch parallel to the z-axis within the helix where the field will not depend on z. We went through that description with the visuals earlier on. And you'll have 2 vertically displaced horizontal branches that extend outward from the z-axis but are located midway between adjacent conductors. The reason why we do this is to basically make use of the periodic symmetry. So for every pitch, you basically repeat the same pattern. And so effectively, this would be the way to set it up. And so if using these 3 conditions basically and a rectangular coordinate, a rectangular contour, we're able to solve the problem. So the conventions, again, applying Stokes' theorem, closed contour integration F dot TdS is equal to a flux calculation, that is the surface integral of the flux density, current flux density, a surface area vector, where the surface basically is the one that's bounded by the contour. So the 2 things, the right-hand rule states that the fingers of the right hand are in the direction of the contour traversal, indicated by TdS. And thus, by default, the thumb points in the direction of the differential area vector ds enclosed by the contour. Usually it is convenient to choose the thumb to point in the direction of j, and thus by default the fingers point in the direction of the vector field f. All right, so now we're going to formulate the solution in Cartesian and cylindrical coordinates. So in Cartesian coordinates, we basically have done a trace. So this basically is the ZY plane. And if we do the ZY plane, what we have on this side basically are the filaments poking out of the page. That's the currents coming at me, and here the current's going into the page. So that's J into the page, J out of the page. Now we've chosen basically, since the current density, we're chosen the contour to be this one here. Now why have we done that? Well, first of all, we know that the current here is going into the page, so we've chosen the area vector also to be into the page. Therefore, by the right-hand rule, the field on the inside will be pointing upwards, and the tangent vector will be going in a clockwise direction. Now, you could have gone and used it, applied it differently. The results would still be the same. As long as you're using the right-hand convention, essentially the final answer will still be the same. But in this case, because the thumb was pointing into the page, the contour integral was in this direction. Because J is into the page, that means that the field on the inside is also pointing in the positive Z direction. There are 4 different segments here that we've chosen. On this segment, the field is uniform. On this segment, the field is perpendicular to the tangent vector. And here also the same thing. And this is the periodicity we're talking about. You notice that this line is halfway between the 2, and this line here is halfway between the 2. And out here, the field is vanishingly small, so its contribution to the closed contour integral you can neglect. So this is how you would set it up if it was a Cartesian coordinate problem. If it's cylindrical coordinates, then r only exists for r greater than 0. So basically we only consider everything to the right. So this would be z, this would be r. And theta now would be basically into the blackboard. So in this case, if theta hat's pointing in the same direction, right, which would be in the direction of the area vector, which is theta hat. And this differential area then would be theta hat dr dz in cylindrical coordinates. F basically is still in the same direction, but we're only concerned with the portion which is for r greater than 0. So nothing has changed here. I mean, this picture is the same, except for this case, we include the left-hand side and the right-hand side. Here, only for r greater than 0 is a solution value. In fact, if you've chosen different values of theta, you essentially end up with the same picture. It doesn't matter what theta is. Okay, so this is the picture that we work with in terms of doing the computation for Stokes' theorem. All right, so now we go ahead and do the computation. So the closed contour integral involves 4 segments. So we have f perpendicular to ds2 and f perpendicular to t4, which were the 2 horizontal branches. We have f parallel to d1 ds, f being uniform, and that's basically inside the helix in the z direction. And for the TD segment outside, f we said is approximately equal to 0. For an infinitely long helix, it would be equal to 0. And z is the vertical height of the contour that we've chosen. And again, we made sure that we always capture periodicity. So the contour integral in this case, given that 3 of these will be 0, means that we're only concerned about the portion which is going up the middle of the helix, which is this contour C1 here. All right, so we just need to now do an explicit representation of the contour, because we know that it's basically just a vertical line, and so the position vector would just be 0, 0, z from some lower limit za to some upper limit za plus z. And so this za basically just refers to, the distance between the reference point for periodicity to the first conductor, and this would be basically at some distance z later, which again would obey the notion of periodicity. So it would be, final position would be halfway between two of the filamentary conductors. If we want TDS, then we have to take basically the derivative of this with respect to z. ds, this becomes 0, 0, 1 dz. So this is the tangent vector representing the contour segment that's inside the helix pointing in a vertical direction. Okay, so in this case, basically, we now have to compute what f would be. We don't know what its value is. We know it's a constant, and we know it's in the z hat direction. So we can write it in this fashion. So it's this value that we need to compute. Again, because it's uniform, we just basically have left it this, but it's going to be a constant value. So if we take f dot t1 ds between lower limit and upper limit, which is determined from here, then this just becomes f of z times z. Again, this f of z is shown generically as z, but it's a constant value. It will not depend on the direction z. Again, za represents the vertical position of the center of the lower winding within the contour with respect to the halfway point between the lower winding and the adjacent winding outside the contour. That was our reference starting point. Okay, so we've now basically set things up on the left-hand side, and so now we need to compute the right-hand side, which involves current flux density and the differential surface area, basically over the area bounded by the contour that we've chosen. N is the number of turns enclosed by the contour. Z is the vertical height of the contour, and A, which is Z divided by N, is the winding pitch. Okay. Now, because we have filamentary wires poking through our surface, we're going to need to use a Dirac delta function to find J, since the current flux density exists for only specified values of R and Z and is 0 elsewhere. And since we formulate the problem both in Cartesian coordinates and cylindrical coordinates, I've written them out for both cases. So for the case of J in Cartesian coordinates, you'll notice from the earlier picture that we had enclosed 3 windings. And so N basically will be an index that runs from 1 to 3. But if we had chosen the contour to include more windings, then N would just run to a higher level. And so what we're doing basically was taking a contribution due to each filament within the area bounded by the contour. And each filament has a position Y and a position Z. And so depending on the index K, we're basically pointing to a different filament that's bounded by the contour. The area ds is minus x hat dy dz. Don't forget the area vector was pointing into the blackboard, so it's minus x hat dy dz. If we were looking at our special case n equals 3, then this expands only to 3 terms, and we end up with this expression that you see here. And again, here also, j is pointing into the blackboard, and so that would be in the negative, this would be into the negative x direction. Okay, so that's why the minus sign, x hat there. Okay, so next thing then is to look at, so there are the 3 windings, 1, 2, or filaments. In cylindrical coordinates, we're only dealing with R and Z. Okay, and so in this case, looks very similar, and the only difference is theta hat's positive, so there's no negative sign here, and the area vector is also in the same direction of theta hat. So this now becomes dr dz, because this is the differential area element in cylindrical coordinates. If we then basically sum to 3, because there are only 3 windings enclosed by the contour, then we end up basically with this expression representing J. Now, J basically, as I mentioned before, this is for a line filament. This is how you would represent it in Cartesian coordinates, which is sort of what we've done here. But because Z and R basically is in a plane, the only thing that changes here is that X and Y basically get replaced by Z and R. In our case, cylindrical coordinates does not apply because we basically have a problem where it suffices to use something that's very akin to Cartesian coordinates. All right, so next step basically is put it together. So we now do the integral of J dot n ds between ZA and ZA plus Z. And Y basically will go from 0 to some value just greater than R, because beyond the filament, basically there's no more contribution. We've encapsulated the whole properties of the filament. So we're integrating basically this vector, dot product with this vector, dy dz. If you do this integral, we know that when you integrate with respect to delta, you get 1. All right, and so this means that each one of these filaments basically makes a single contribution of 1, which means the total contribution will be 3. There's a minus here and a minus here, so that's why we end up with positive 3i. If you do it with cylindrical coordinates, in this case, it was theta hat and theta hat, dr dz, but again, similar outcome. Final value is 3i. All right, the next step is to equate the left-hand side with the right-hand side to compute the vector field F. And so in both Cartesian and cylindrical coordinates, we end up with a similar expression that f of z, again, this value is a constant. I've shown it just as f of z equals 3i. Therefore, f of z will equal I times 3 divided by z, which means it's a constant value. The numerator on the right-hand side of the equation is the number of turns n enclosed by the contour. Hence, in general, the right-hand side of the equation can be written as f of z equals I, n divided by z, but this is nothing more than I divided by the pitch of the winding. So n over z is equivalent to the pitch of the winding. The units are 1 over meters. Okay, so now we know that the field is pointing in the z hat direction inside and 0 outside. And we know its magnitude is I over A, and so now we can write out the full expression that F is equal to I over A Z hat for x squared plus y squared less than r squared, and is equal to 0 once you're outside the circle. Finally, we can graph the magnitude of the field parallel to the z-axis and inside the helix in cylindrical coordinates. So you can see basically its value is constant until you get to the edge, more or less, right? And then basically drops to 0. This being the radius in our example. This example problem, I chose the radius to be 1, current to be 4, and the height of our contour to be equal to 6. And so this is basically the result that we got. All right, so that concludes lecture 29. Thank you for listening.